Hello students, welcome to the lecture on adaptive filters. Let us note that we discussed Wiener filter and its application to linear prediction in last few lectures. Wiener filter is an LTI filter, linear time invariant filter, and it works on the assumption of WSS signal, wide sense stationary signals. The filter coefficients are determined from the knowledge of the autocorrelation and cross-correlation functions of the signals used. In practical situation, the signal is non-stationary. Under such circumstances, optimal filter should be time varying. Now, how to tackle this non-stationarity? One way to tackle non-stationarity is to assume stationarity within a certain data length. For example, in speech coding purpose, the signal is assumed to be WSS during a few milliseconds. This approach has a drawback. The time duration over which stationarity is valid may be short, so that accurate estimation of the model parameters is difficult. Next solution is the adaptive filtering. Here the filter coefficients are updated as a function of the filtering error using an adaptive algorithm. So, in adaptive filtering we have an adaptive algorithm which will update the filter coefficients as a function of the filtering error. The adaptive algorithm updates the filter coefficients based on the input signal and other relevant information to obtain optimal performance. This lecture will cover the basics of adaptive filters. The general setup for adaptive filter is as shown in this figure. So, here Yn, this noisy signal, is the input to the adaptive filter, and there is the adaptive algorithm, and d hat n is the output of this adaptive filter. The adaptation of the filter coefficients is based on the error En between the filter output d hat n and a reference signal dn, usually called the desired signal. Now, in the adaptive filter terminology, we have a desired signal. We have a desired signal dn, and the difference between dn and d hat n, that is the error. This error is sent to the adaptive algorithm for updating the filter coefficients, and these filter coefficients will be used in this adaptive filter. Choosing dn, how to choose this desired signal dn is tricky. It depends on the specific application. This adaptive filter may be FIR with known filter length, or it may be IIR. The FIR filter structure is normally used. The adaptive algorithm updates each FIR filter coefficient individually. We saw the general setup for adaptive filtering. Here Yn, that is the input, it passes through the adaptive filter to estimate the desired signal, and this estimated signal is compared with dn, and the error is passed to the adaptive algorithm to update the filter coefficient, and these updated filter coefficients are used here. So, this is the basic setup for adaptive filtering. We will see how the desired signal dn can be obtained in different applications. First one is system identification. Here this is the system with unknown model parameters. So, we have to identify the model parameters, that is the system identification problem. And here a broadband signal Yn, usually a white noise, is input to both the system and the adaptive filter. Then the output of the system is the desired signal dn. So, this dn is passed through the for error calculation. So, the adaptive filter will estimate d hat n, and the error will be computed. This error E n will be now used to update the adaptive filter coefficients. That block we have not shown, but this error will be sent to the adaptive filter algorithm to compute the filter coefficient iteratively. So, that way this is the adaptive filter used for system identification. When the adaptive filter algorithm converges, the corresponding filter parameters will give the linear model of this system. So, therefore, at convergence, adaptive filter gives the linear model of the system. We will consider another application, channel equalization. It is used to cancel the effect of this channel. Training signal is sent through the channel. This is Xn is the training signal. Suppose it is again it is a white noise usually, and through some delay operation we will get the desired signal. In this case, the receiver knows this signal, and Xn, the training sequence is passed through the channel, noise is added here. So, we will get Yn, and this Yn is passed through the adaptive filter to estimate d hat n. So, we will get d hat n here, and now this error will be passed to the adaptive algorithm to compute the filter coefficients iteratively. So, that way we saw that this adaptive filter now can cancel the effect of the channel. At convergence, the adaptive filter cancel the effect of the channel. When this noise is not there, this adaptive filter will be the inverse filter corresponding to this channel. So, that this channel equalization basically we can say that it finds an inverse filter to cancel out the effect of channel. Now, we will consider one important algorithm, what is known as the steepest descent algorithm. FIR winner filter and steepest descent algorithm. Assume the signals to be WSS. Here in the adaptive filter structure, we assume that Yn and suppose Dn, they are WSS. Our goal is to estimate Dn using an FIR winner filter of length m and the filter coefficient Hin I going from 0 to m minus 1. I is the index for filter coefficient, and this n may be time or it may be representing the number of iterations in the case of iterative algorithm. Represent the filter coefficients by the filter parameter vector Hn vector, that is equal to H0n, H1n up to Hm minus 1 n. So, this is m length filter coefficient vector. Our goal is to find Hn by minimizing the mean square error, and mean square error is expectation of E square n, that is E of Dn minus d hat n whole square, that is equal to E of Dn minus summation Hi n Yn minus I going from 0 to m minus 1 whole square. Now, we represent this optimization problem in the matrix form. For that, we represent Yn as this vector. Yn vector is equal to a vector comprising of Yn, Yn minus 1 up to Yn minus m plus 1. Therefore, E of E square n is equal to E of Dn minus H transpose n into Yn whole square, and that is equal to E of D square n minus twice Dn into H transpose n into Yn plus H transpose n Yn transpose into Hn, and after taking the expectation we will get first term will be Rd0, similarly second term will be 2 H transpose n into Rdy plus Hn transpose into Ry into Hn. So, this is the mean square prediction error. The winner filtering problem can be written as minimize E of E square n with respect to the filter coefficient vector Hn. The cost function represented as E of E square n is a quadratic function in terms of Hn, and therefore a unique global minimum exists. Here we are illustrating with the help of a 2 parameter filter. So, this is H1, H2 and this is the MSE. If we plot MSE versus H1, H2, we will get a quadratic surface like this. For this surface, one optimum will exist. The gradient of E of E square n is given by gradient of E of E square n. E of E square n is a scalar, gradient is a vector. So, this is equal to del H naught of E of E square n. Similarly, next element will be del H1 of E of E square n, like that. The last element will be del E of E square n del H m minus 1. And if I compute this vector from this expression, if I now take the partial derivative, this term will go down to 0. So, that way we will get this expression minus twice r dy plus twice ry into Hn. For the minimum, gradient of E of E square n is equal to 0. So, that we get the Wiener-Hoff equation ry into H optimum is equal to r dy. So, autocorrelation matrix into coefficient vector is equal to cross correlation vector, and we can get H optimum by this relationship ry inverse into r dy. Instead of this analytical solution, the optimization problem in this optimization problem can be solved iteratively. One of the iterative optimization algorithm is the steepest descent algorithm, SDA. The most of the popular adaptation algorithms, including machine learning, are based on the SDA. So, that way SDA, steepest descent algorithms, are very popular. From machine learning to deep learning, this algorithm is used. Now, let us see how SDA iterations are done. Since the gradient of a function points to the direction of maximum increase of the function, the negative of the gradient is the direction of maximum decrease of the function. This is the logic. So, negative of the gradient gives the direction of maximum decrease of the function. Applying SDA, the optimization problem can be now solved by the following iterative relation. H of n plus 1 is equal to earlier Hn plus mu by 2 multiplied by negative of the gradient. Now, this 2 is just to scale this part. Generally, this part will give a 2 terms to cancel that, we have used 2 here, but mu is the step size parameter or learning parameter. So, this steepest descent rule will now give H of n plus 1 is equal to Hn plus mu times r dy minus ry into Hn. By computing gradient of E of E square n, we get this expression. For a proper choice of mu, this SDA solves the Wiener-Hoff equation in a finite number of iterations. Now, let us discuss about the convergence of the SDA. We have H of n plus 1 is equal to Hn plus mu times r dy minus ry into Hn, and this we can rewrite as Hn minus mu times ry into Hn, then plus mu times r dy, and if I take Hn as common, this will be I minus mu ry into Hn plus mu into r dy, where I is the m by m identity matrix. Therefore, the SDA iteration step can be written as H of n plus 1 is equal to I minus mu ry into Hn plus mu r dy. Expanding this expression we get, suppose this one is the Hn plus 1 vector and this is the I minus mu Ry matrix and this is the Hn vector. Hn plus 1 equal to I minus mu Ry matrix into Hn. This is I minus mu Ry matrix plus mu times this R dy vector. From this we see that the SDA iteration is given by a coupled set of linear difference equation. For example, the first difference equation will be H0 n plus 1 equal to this row multiplied by this column. So, it will involve all these coefficients plus mu times R dy 0. So, that will be the first equation which involve all the filter coefficients in the previous stage. So, that way it is a coupled set of linear difference equations. For convergence analysis, we want to represent this set of difference equation into a uncoupled set of difference equations. So, for that we do this similarity transformation. Ry is a symmetric non-singular matrix and can be diagonalized by the following similarity transform. Ry is equal to Q lambda into Q transpose, where Q is the orthogonal matrix of the eigenvectors of Ry. Lambda is a diagonal matrix with the corresponding eigenvalues as the diagonal elements. So, Q is the matrix of the eigenvectors and Q is orthogonal. It means Q transpose Q is equal to Q transpose is equal to identity matrix, that is the orthogonal matrix. So, that way in this expression we can write Ry as Q lambda into Q transpose. Also this I matrix we can write as Q into Q transpose. Identity matrix can be expressed as the product of Q and Q transpose. So, that way because Q transpose is Q inverse and that is equal to Q transpose into Q. Therefore, the SDA iteration H of n plus 1 is equal to I minus mu Ry into Hn plus mu R dy. This iteration can be written as H of n plus 1 is equal to Q transpose minus mu Q lambda Q transpose into Hn plus mu R dy. If we multiply by Q transpose both sides, this Q transpose into Hn plus 1. Now, if we multiply by Q transpose, here Q transpose into Q will be equal to I and here Q transpose into Q will be equal to again I. Because of that we can take this Q dash as common and what we will have is here right hand side we will have I minus mu times lambda into Q transpose Hn plus mu times Q transpose R dy. So, this relationship we get by multiplying Q transpose both sides. Let us define new variables, that is H bar n is equal to Q transpose into Hn and R dy bar is equal to Q transpose into R dy. So, in terms of these new variables we will now have H bar n plus 1. So, from this equation this is H bar of n plus 1 and this is equal to H bar of n and this is equal to R dy bar. So, that way we will have H bar of n plus 1 is equal to I minus mu lambda into H bar of n plus mu times R dy bar. So, expanding this we can write this has first term will be 1 minus mu lambda 1 and rest of the terms will be equal to 0. Similarly, here this term will be 0 and next term will be 1 minus mu lambda 2. Like that we can complete this matrix multiplied by h bar of n plus mu r dy bar. Now, this set of difference equations is a decoupled set of linear difference equations and it will be given by h I bar n plus 1 is equal to 1 minus mu lambda I into h I bar n plus mu r dy bar I for I is equal to 1 to m. And this can be easily checked for convergence, because now we have a difference equation like this and this coefficient will determine the convergence. For example, the first equation will be h1 n plus 1 will be equal to 1 minus mu lambda 1 into h1 n plus mu r dy. The convergence condition is given by this: mod of 1 minus mu lambda I is less than equal to 1 for all I is equal to 1 to m. So, this implies that 1 minus mu lambda I lies between minus 1 and 1. So, from this relationship we will get 0 is less than mu less than 2 by lambda I for I is equal to 1 up to m. Thus, the condition for the convergence of the modified difference equations h I bar n plus 1 is equal to 1 minus mu lambda I times h I bar n plus mu times r dy bar I. So, I equal to 1 up to m is given by mu lies between 0 and 2 by lambda max. This is the condition for convergence of this set of difference equations. Equivalently, the SDA iteration h of n plus 1 is equal to I minus mu ry into h n plus mu r dy converges if 0 is less than mu less than 2 by lambda max. So, this will be the condition for convergence for the SDA iteration. We can get a simpler condition. Note that all the eigenvalues of Ry are positive. Let lambda max be the maximum eigenvalue, then lambda max will be less than equal to sum of all these eigenvalues, because all are positive. Therefore, lambda max is one of them and definitely it will be less than the sum of the eigenvalues, and the sum of the eigenvalues is equal to trace of Ry. Therefore, this condition can be written as 0 is less than mu less than 2 by trace of Ry. Also, all the diagonal elements of Ry are Ry 0. Therefore, m diagonal elements are there. Therefore, this expression 2 by trace of Ry will be equal to 2 by m times Ry 0. Therefore, the simpler condition for convergence is 0 less than mu less than 2 by m times Ry 0. So, this is the condition for convergence. So, we have to select mu in such a way that it is less than 2 by m times Ry of 0. Thus, this steepest descent algorithm converges to the corresponding Wiener filter limit h n as n tends to infinity is equal to r y inverse into r d y if the step size mu is within the range specified by the above relations. So, this relation or this relation, if we consider these two relations for limiting mu, then the steepest descent algorithm will converge to the Wiener solution given by this. Now, let us make a comment about the rate of convergence of the steepest descent algorithm. Considering the difference equation h of n plus 1 is equal to I minus mu ry into Hn plus mu rdy. The rate of convergence depends on the eigenvalue spread of the autocorrelation matrix Ry. So, the spread of the eigenvalues of this matrix will determine the speed of convergence. This spread of the eigenvalue is expressed in terms of the condition number, which is defined as k is equal to lambda max by lambda mean. So, if this k is large, then convergence will be slow. The fastest convergence of the system of difference equations occur when k is equal to 1, and this corresponds to white noise. And this also explains why in our system identification problem and channel equalization problem, we took the input sequence as white noise. We will consider one example. Suppose Ry is equal to this matrix, diagonal elements are 21, off diagonal elements are 16, and Rdy vector, that is the cross correlation vector, is 20, 16. We want to determine a length to FIR winner filter using the SDA. Take H0 is equal to H0 of 0, H1 of 0, that is equal to 0, 0, that is the initial value of H0. The eigenvalues of Ry we can determine. Lambda 1 is equal to 37, lambda 2 is equal to 5, and therefore we can choose mu is equal to 0.02, which is less than 2 by 37. Similarly, we can consider, suppose sum of the diagonal elements is 42, therefore we can have a condition that this mu should be less than 2 by 42. So, that way also we can select this mu is equal to 0.02. Using h of n plus 1 is equal to hn plus mu times rdy minus ry into hn, we get h1, that is equal to h01, h11, that will be equal to initial value is 0, 0 plus this is the multiplier 0.02 times r dy vector, that is 20, 16, and ry into hn, that we will get 0, 0 only. So, that way we will get, if we carry out this computation, we will get this as 0.4, 0.32. So, h1 vector is a vector comprising of 0.4 and 0.32. Similarly, after 3 iterations, we will get this value, h3 vector will be equal to 0.5863 and 0.3695, meaning that h0 of 3 will be 0.5863 and h1 of 3 will be 0.3695. In this way, we can continue, and after a number of iterations, we will be getting close to the Wiener-Hopf solution, which is given by h is equal to 0.8865, 0.0865. This is the relationship which we can get by direct matrix inversion. Let us summarize the lecture. The filter coefficients of an adaptive filter are updated based on the error En between the filter output and the desired signal Dn, as shown in the figure. This figure we discussed. So, here this is the adaptive filter, and filter coefficients are determined according to the adaptive algorithm, and input to this adaptive algorithm is the difference between this desired signal Dn and the adaptive filter output D hat n. So, this error is the input to the adaptive filter algorithm, and accordingly the filter coefficients will be updated and fed to this adaptive filter. The cost function E of E square n for an FIR winner filter is a quadratic function in Hn, and a unique global minimum exists. Now, the optimal set of filter parameters can be found by the SDA iteration that we have established. H of n plus 1 vector is equal to Hn vector plus mu by 2 times minus gradient of E of E square n. And under WSS assumption of the signals, we get H of n plus 1 is equal to Hn plus mu times R dy vector minus Ry matrix into Hn vector. We also established that the SDA iteration converges if we select mu to be less than 2 by lambda max, where lambda max is the maximum eigenvalue of the autocorrelation matrix. A simpler condition is obtained, that is 0 is less than mu less than 2 by trace of Ry matrix, and this trace is equal to m times Ry of 0. Therefore, the SDA iteration will be convergent if we select mu less than 2 by m Ry 0. In SDA iteration, the filter coefficients converge to the winner solution, that is limit of Hn as n tends to infinity is equal to Ry inverse into small r dy if the step size mu is within the range specified by the above relations, that is this relation and this relation. Note that we applied the SDA to solve a deterministic optimization problem, that is minimize E of E square n with respect to the filter coefficient vector Hn. The optimization problem is reformulated as minimize, instead of E of E square n we will write E square n with respect to the filter coefficient vector Hn. The above problem is solved by the SDA, resulting in a powerful adaptive filter algorithm, namely the least mean square LMS algorithm. We will discuss the LMS algorithm next. Thank you.